I guess they even make a 384 well version of this. Now I couldn't find a picture online. So, these chips are still amazing. I got my start 15 years ago, analyzing, I guess, the first couple dozen of these with Todd Golub at the Whitehead Institute, and Zach Kohani out of Harvard. But to me, the most amazing part of these chips, right, isn't the chip. I mean, they're a couple $100 now. It's the fact that so many researchers use these chips that in the early 2000, 2001, 2002, the top journals start to realize they were getting inundated with these papers. Here's a list of genes changing in that disease. Here's a list of genes changing in that cancer. And it started with the top journals. They said, hold on a second, no more papers with these chips. No more. Unless you put your data into an international repository where other people can double check your math and maybe someday reuse those samples for something else. And that's the world we're in today. So we are in this world where we can reuse samples. Fast forward to today, right? This is as of maybe a couple days ago. When you look online at these two repositories, one's run by NIH in the back, Gene Expression Omnibus. Array Express is run by the Europeans. We've got 1.7 million of these chips publicly available today. 1.7 million of them. Still doubling, let's say every 2 to 3 years. Just in this 1 hour or hour and a half, we'll probably add another 100 samples, right? Just while we're sitting here. And all that data is waiting for you, waiting for someone to do something interesting with that, right? So we can get lost in the millions and billions and trillions. Let me just say how amazing this is, right? In the middle of this website is a search box, right? And some of you have heard me say this before. Any one of you, forget about you. Any high school kid, right, who needs to do a science fair project, right? Any high school kid can go to this website, she can type breast cancer, and find and download 50,000 samples of breast cancer for her research project, about as easy as she can find a song on iTunes today. This is here and now, today. Actually, 50,000 is an interesting number. The number above that is more interesting. 2,000 labs have already contributed data, 2,000 independent labs, right? Now, why is that amazing to me, right? Let's think about it this way. Let's say I'm a brand new researcher in breast cancer, right? And I'm writing a grant. And I want to get 2,000 of the best labs to give me data, right? You're all the review committee on my grant, the study section. And I'm proposing to you that I'm going to get 2,000 of the very best labs in the world to use the latest technologies in the world on their most characterized patients and give me all that data for free, okay? If I were proposing getting your friends on the internet to help, that's called crowdsourcing. If I were to propose this in a forward direction, you would laugh me out of the room. Why would 2,000 researchers help a complete newbie like me for free? Yet here it is. 2,000 labs are helping me for free. So when I think of open big data, I think of it as retroactive crowdsourcing, okay? What does that mean? 2,000 labs are there to help you, and those labs don't even know they're helping you, right? Actually, 2,000 labs are there to help you, and you don't even know they're helping you. And if for some reason 50,000 samples aren't enough for you, just wait another 2 or 3 years, it'll be 100,000 samples by doing nothing. What an amazing world we're in today. All of this data is sitting there waiting for you, whether it's RNA or DNA, many repositories we'll talk about as we move forward. Now, if any of you have any doubts a high school kid can do it, here is the high school kid that did it, right? I still yet to meet her, Brittany Wenger, who's now at Duke. She was at Sarasota, Florida, who won, I think this was 4 years ago, the top Google Science Fair competition for developing an artificial brain or neural network, machine learning, for breast cancer. I guess she got bored the next year. She was in all the front pages for doing it again for leukemia. And so, of course, a high school kid can do this. And of course, what I mean by that is if a high school kid can do it, all of us should be able to do this, right? At least in our academic institutions, this is legitimate science, starting with the data of others. So we've had this idea that we can use this data. I'm going to give you a diagnostic story, and then I'm going to give you a therapeutic story. And the first diagnostic story is we realized, my first big grant from NIH was don't go make more microarrays, go collect all the microarrays that have ever been run looking at human diseases. And we collect experiments like this, where you have diseased individuals and healthy controls, and someone's run a microarray in each one of these samples, regardless of the disease. We start to compute. I'm going to show you genes or numbers. I'm showing you colors. I'm going to compute these differences, these signatures. Now, in reality, you can take almost any disease, and many labs have already studied it. And we start to realize we can put those data sets together, a term called meta-analysis. And to make it really simple, the idea here is if one lab sees a gene up, that's interesting. But when all of the labs see the same genes up, maybe that's even more interesting. Maybe it's causal in the disease, or at the very least, maybe it's reliable, robust. It could become a blood test for this disease. Now, for